Is my screen visible?
Yes, sir.
That's correct. Okay, so today I'll first discuss the three problems that are remaining from the tute sheet, and then I'll be discussing with one or two more doubts which somebody have, like most of you have asked me, that I'll be discussing. So without wasting any more time, let's start. So we were remaining with possibly which questions from the tute sheet. Let me check. We're remaining with possibly 3, 4, and so on, right? 3, 4, and 5 was remaining. Okay. So let me write it down. So for doing those things, I have to state few theorems and all. So let's start with stating a theorem. So if a function fz, which is u plus iv, is analytic in a domain D, then its component functions, which is u and v, are harmonic in. So this is not a difficult theorem to prove. It's very easy. Let me write this down. I don't know. Okay. Anyways, so if a function is analytic in a domain D, then its component u and v are harmonic in D. So what is the meaning of harmonic? I'll first explain what is the meaning of harmonic. So what is a harmonic function? A real valued function h of, could you excuse me for a minute, just a minute. Just wait for 5 minutes, okay? Just 5 minutes. Sorry for the inconvenience. Right. So I was talking about what is a harmonic function. So real valued function h of two real variables, x and y, is said to be harmonic in a given domain D of the xy plane if h has continuous partial derivatives of the first and second order in D, and h satisfies hxx plus hyy is 0, that is h satisfies the Laplace equation. This equation is called as Laplace equation. So Laplace's equation. Okay, I'll first explain these two things. So what is a harmonic function? So real valued function h of two with real variables x and y. So this time we are talking about real valued function, and the variables are x and y are also real numbers. Okay, so real valued functions h of two real variables x and y is said to be harmonic in a given domain D of the xy plane. So when will I say that this function h is harmonic in the xy plane? If h has continuous partial derivatives of first and second order, and h satisfies this partial differential equation, hxx plus hyy is 0, that is h satisfies the Laplace's equation. Okay, now what does the first theorem state? That if a function fz is analytic in a domain D, then this u and v, they are harmonic. That means they will satisfy this relation. Okay, they will satisfy this relation, keep that in mind. So proof is not that difficult, you can do the proof by yourself. Just remember, if a function is analytic, that will satisfy the Cauchy-Riemann equation. You can differentiate it partially with respect to x and y again, and you'll get this kind of thing. But this is another condition to be harmonic, that it should have first and second continuous partial derivatives. So that can also be proved. So I'll be using this theorem for doing a particular question. Okay, so remember this, I'll be using this theorem for the timing to do a particular question. So firstly, I would like to do this question, number 4. I will do number 4 from the tweet sheet. So before going to number 4, do you know what is the meaning of contrapositive statement? So if I have a statement P implies Q, what is the contrapositive of this statement? Can anybody tell me?
Not Q implies not.
Right, contrapositively. This is same as saying negation Q, that is not Q, implies not P. So what is the contrapositive statement of the above theorem? Can anybody tell me?
If U and V are not harmonic.
Sorry, yeah, somebody was speaking something. Yeah.
If U and V are not harmonic, then Fz is not harmonic.
Not analytic, right? So correct. So remember, this statement says that if U and V are not harmonic in D, in some domain D, then the function fz, which is u plus iv, that cannot be analytic. So number 4, The question was,
So U and B or U or B?
U, right, U or V. If any one of them, that's correct. That's correct. Thank you. If U or V, if any one of them is not harmonic, then the function cannot be analytic in that particular domain. So in number 4, the question was, this was given that U x comma y was x square plus y square, and you have to find all those analytic functions whose real part can be this. Okay, you have to find all those analytic functions whose real entire function maybe whose real part is this, but there will exist no such entire function whose real part is this, because this function is not harmonic. You can check that. So what is the first partial derivative with respect to x? It is 2x. And what is u xx? It is 2. Uy is 2y. Uyy is 2. Uxx plus uyy is actually 4, which is never 0 in any domain. So what can I say? Therefore, there exists no entire function fz whose real part u is this. So did you get my point? Any confusion? Okay, so whenever you are given some real part, do not proceed blindly. First check whether that is harmonic or not. If it is not harmonic, the function cannot be analytic. Keep that in mind. So what is the another theorem? So for going to the next question, so let me write that. So what is called as harmonic conjugate? So harmonic conjugate. So this is required to do the next question. If given two functions, u and v, are harmonic, in a domain D, and they satisfy the Cauchy-Riemann equation, that is ux equals to vy and uy is equals to minus vx throughout D, then V is said to be harmonic conjugate. So this is a particular term, harmonic conjugate of U, and U is said to be the harmonic conjugate of V. So if I have two given functions U and V, and they both are harmonic, and they satisfy this relation that ux equals to vy and uy is equals to minus vx, then this function v is said to be the harmonic conjugate of u. Okay, and what does the next theorem says? This is again very easy to prove. A function fz, which is u plus iv, is analytic in a domain D if and only if V is a harmonic conjugate of u. So this is another very easy theorem, we can prove it. So whenever I have an analytic function u plus iv, if that is analytic, then v is the harmonic conjugate of u, and conversely also this is true. If I have some function u and v is its harmonic conjugate, then using u and v you can find an analytic function u plus iv. So using this theorem, we'll go to the remaining problem, which was number 3. So what was the theorem? Again, the same question was there. So let me just check the question once again. Hold on. Problem set 1. Yes, the question was find all entire functions f equals to u plus iv such that u is x square minus y square. So the above question is also same. uxy was given. Here also uxy was given, is given, right? But here u is not harmonic, and as a result of which there will exist no such entire function whose real part is that. But here if you check, you first always check that u is harmonic or not. So if I check what is ux, it is 2x, uxx is 2, uy is minus 2y, uyy is minus 2, and uxx plus uyy is always 0 in whole of the xy plane. So this implies u is a harmonic function. Right? U is a harmonic function. So there might exist or there will exist an entire function. Why entire? Because this equation holds in whole of xy plane. So there will exist some entire function whose real part will be u. So how can you find such an entire function? You have to find the harmonic conjugate of that real part u. So remember, is a harmonic function, harmonic conjugate. So there can be many harmonic conjugates. So one of them is v. So the next task is to find the harmonic conjugate of this real part. Idea is very simple. How to find the harmonic conjugate? You see, they must satisfy this relation. They must satisfy this relation. Ux equals to vy and uy is equals to minus vx. So I'll just find that. Okay. So let v be a harmonic conjugate of u. So then, because v is a harmonic conjugate, then what I have, ux equals to vy and uy is equals to minus vx. So just put down the values. So from the first equation, what I have, vy is nothing but ux. What is ux? Ux is 2x and vx is minus of uy is minus 2y. So that will become plus 2y, right? Could you please check once? Am I right or not?
Yes, sir.
Okay. So look here. I will integrate partially with respect to y. So this will give me v is equals to. So this will be treated as a constant. I am differentiating. I am integrating partially with respect to y. So this will give me. This will be treated as a constant. So 2xy and plus some constant. That
Function
constant.
of x.
Right. That will be a function of x. You can check if you differentiate this partially with respect to y, you will get this line. You will get this line. So remember, whenever you will integrate partially with respect to x, you will get a constant which will be in terms of x. So I have got the value of v from this equation. This is still remaining. I will plug this value here. Okay. So for that, I have to first find what is vx. So therefore, Vx will be partially differentiating with respect to x. So this is this, and this is the derivative of x. So if I call this as some equation 1, if I call this as 2, from 1 and 2, so what will we obtain from 1 and 2? That
h dash of x equal to 0.
Right, h prime of x is 0 or h dash of x is 0. And what will that mean? That h is a constant.
Hx
Hx is a constant. Suppose I'm calling that constant c, and remember this is a real constant, right? This will be a real constant because h is a real valued function. So therefore, I have calculated v. What is v? V is equals to 2xy plus c. And you may check that v is also harmonic. That you can simply check. Okay, just a minute. I'm getting. Sorry again. Am I audible now?
Yes, sir.
So you may check that V is harmonic, and V is the harmonic. V is a harmonic conjugate of U. For different values of C, I'll get different harmonic conjugates of U. Okay, that is the reason I've written a harmonic conjugate. So what is F in that case? So what is F? So therefore, my function F U plus IV, right? So U plus IV, U was x square minus y square. Okay, so U is x square minus y square plus IV, V is 2xy plus C. This is x square. I can write this as plus IY whole square plus 2xIY plus C. The first part is what? X plus IY whole square and plus, sorry, this will be IC. So this is nothing but Z square plus IC. So I have calculated, I have found out all the entire functions whose real part is this. So therefore, all entire functions whose real part is uxy equals to x square minus y square are fz equals to z square plus ic, where c is any real constant. Remember that, because the c was here. Okay, any question? Okay, so this was 3 and 4. See, if you look at the questions, they were almost same. But remember, before proceeding, you have to first check whether the given function is harmonic or not. This was harmonic, so I proceeded. But this was not harmonic. I did not calculate the harmonic conjugate. It will not exist. Okay. So we have the next similar question, number 5. So what is the question of number 5? Let f is equals to u plus iv be an entire function such that fz is a function of x comma y, and which is ux plus ivy. So this function is entire, that is, it is analytic in the whole complex plane, and its real part consists only of the function of x, and the imaginary part consists only of the function of variable y. Show that f is a polynomial in z of degree less or equals to 1. So again, we'll use the same theorem because this function is entire. What I know that its real part and its imaginary part must be harmonic, and they will satisfy the Cauchy-Riemann equations. That is simple. So solution, as f is entire, we have ux is equals to vy and uy is equals to minus vx, and this will hold throughout C because this is entire function. This equation should hold throughout the whole complex plane. Now u being a function of x, ux means du dx, because this has only one variable and that is x, and I am differentiating partially with respect to x, which is same as differentiating it with respect to x. And similarly, v being a function of y alone, so this is also same as writing dv dy throughout C. Okay, and this will result in nothing. This will give you 0 equals to 0 because you have a function of x, you are differentiating it partially with respect to y, you'll get 0, and this is also 0. So this is trivially true, no need to write. Okay, what can you say from this line? Can you say something from this line?
Yes, sir, both are constant.
That's correct. That's correct. This is completely a function of x and this is completely a function of y. If you differentiate u, you'll get another function of x, you'll differentiate v with respect to y, you'll get some function of y, and they are equal. When will a function of x equal a function of y? If and only if they are constant. So this should be equal to c, right? So this implies a constant basically. So what will this give me? Du dx is c and dv dy is c. This will own me, let this property du, right? So what is u from here? Cx plus another constant. Suppose I'm calling that constant as k1, and v is nothing but cy plus another constant k2. You justify, okay, where k1 and k2 are some real numbers. They all are real constant because u and v are real valued functions. Okay, so in that case, what is my function f? So fz, which is nothing but u plus iv, this becomes cx plus k1 plus I cy plus k2. This is c x plus iy plus k1 plus I k2, and this is c times z, and this is some complex number k, where k is k1 plus I times k2. So you see what I have got. Therefore fz is nothing but cz plus k, which is a polynomial of degree lesser equals to 1. Why lesser equals to 1? Because when c is 0, c can be 0 as well, because we don't know anything about c. When c is 0, so the degree in that case will be less than, we will be 0, which is less than 1, and if this C is non-zero, the degree is 1. Then proved. Any confusion? Okay, so I have completed the tute sheet. So I'll do more 1 or 2 exercises, some like those who have asked me. So one thing I'll be doing is normal convergence, which was left as an exercise. Some of you have asked me this doubt. So normal convergence implies uniform and absolute convergence. I'll be doing uniform convergence part. Okay, so has anyone tried this? Nobody has tried this? Okay, so I'll assume it that is a no. This is not at all difficult, it is very easy. This revolves only around the definitions. If you know the definition of normal convergence, if you know the definition of uniform convergence, we are done. So I'll first write down the definition of both the things. So what is the normal convergence? So let Fn be a sequence of functions from x to c. This is exactly what is given by sir. I'm just writing it. Be a sequence of functions on a set x. We define norm of Fnx like this, which is supremum of x in x. So this is a basic definition of a norm. So we say that this series of function is normally convergent if the series of non-negative real numbers this converges, that is this sum is finite, that is this converges. So understand this definition properly, you will get the thing. Look at this guy, this. So norm of a function is nothing but supremum of modulus of all the function values. So I hope you understand this. Remember, this is a real number. So given any function, this is going to be a real number. Okay. So we say that this sequence of function is normally convergent if this real sequence converges. Okay, so we are comparing a series of function to a series of real numbers. Okay, so remember that we say that this is normally convergent if the sequence of this real number is convergent. Series of real number is convergent. So this is the definition of normal convergence. And let me also write down the definition of uniform convergence of series of sequence of function. I'll write down the Cauchy criterion. Okay, so this is Cauchy's criterion. A series of functions fn from x to c is uniformly convergent on x if and only if, or if I'm writing the definition, okay, so if and only if for each epsilon greater than 0 and for all z coming from the domain which is x, there exists some k in n such that modulus of f of k plus 1, okay, of z. This is less than epsilon for all n greater or equals to k. Greater than k, I can also say. So I hope you all have seen this Cauchy's criterion while doing this sequence and series of functions. So I should write like this: a series this fn. Okay. So what I have to prove? Suppose a series of function is normal convergence, that will automatically imply uniform convergence. So proof. Now I'll start with the proof. So what is the proof? It is simple. Let summation fn be normally convergent. Fn's are from x to c. So therefore, by definition of normal convergent, this will be convergent, right? That is summation fn norm of fn, this converges. This series of real number converges. Now look at the definition. So you have done real analysis and just look at the definition of this thing. So can somebody tell me that this is a real series? This is a real series and this means it converges. So when will a real series converge?
When sequence of partial is convergent.
Right. So if you take the partials in that way, so let Sn is equals to norm of f1x up to norm of fnx. So this is the sequence. If I consider the sequence Sn, then that is a sequence of partial sum. So therefore, for any epsilon greater than 0, there will exist some natural number k such that this Sn minus Sk is less than epsilon, right, for all n greater or equals to k. So if you use this condition, that is, so what is Sn minus Sk?
Is
It is
Fn norm of
Fk
Fn
plus
plus
1
1.
plus Fk plus 2 dot Fn.
normal plus up to Fn, right? and I will not write this modulus because they are already non-negative by definition, right? So this norm is useless, so this modulus is useless, so sorry. So Sn minus Sk will be this. So this condition is given to us for all n greater or equals to k. Now it's very simple. I want to show that it is uniformly convergent. I have to prove this. I have to prove this line, right? It's extremely simple. So now let some z in the domain, and we will start with this thing. We'll start with this thing. So then modulus of f of n, sorry, k plus 1 z, k plus 1 z plus up to f n z. Then for all n greater or equals to k, this by triangle inequality, this is lesser or equals to now. Who can tell me the next line from here? Sorry?
Which is less than supremo.
Less than
Right.
epsilon.
Because no, before that, you know, this is nothing but the supremum, right? So this thing will be less or equals to this thing for every x in x. So this is the main thing here. So what can I say from here? This is less than, you can also write, okay, I write equals to also. So this is norm of fk plus 1 plus norm of fn, because by the definition of norm, just look at the definition of norm, each component will be less than the supremum, and this is again by this condition here, this is less than epsilon, right? So therefore this is uniformly convergent on x. This is the end of the proof. Okay, so I'll stop the recording and then we'll discuss few more things. If you have some doubts, let me stop the recording.